Ask me how I know this. Let's do some holes and roundovers on the K&T 2D rotary head mill. Starting this off by cleaning up the outside faces of a couple of scraps, and I really mean scraps, of 3-inch by quarter-inch angle. And the underside of this angle was really pitted, which is going to come back and bite me a little bit in the end, despite cleaning up the outer edges as I did in this shot here. On the other side of the leg of this angle, you can see a hole that I put in with the old drill press and a hole saw to try to get some features on this for a project that I'm working on, and it just was not accurate enough for what I was trying to do. So we can do a little bit better now that we have this mill. So basically doing the same treatment on this this face and this front edge here. I think you get a kick out of this. Watch what happens in the bottom of the photo. This is the elevating screw. I took the cover off because I was worried about this thing getting lubrication. Not so worried about it now, seeing that positive jet coming and flooding all the gears. And here's the cover that was on in place of that ground to be flush with the top of the ways. This mill is a 4-inch long by 7/8 diameter roughing cutter from Haneda. It's not carbide, it's high-speed steel, titanium nitride coated. And what I'm doing is, clamping these angles. You just scrap in at a 45, which allows me to walk across those ends and get them square without taking a big long 4-inch cut. So I'm going to touch off and take about 10 thousandths initially until this edge cleans up. You can see I'm touching here and I'm not touching there. And really, for a roughing cutter, that's not a bad finish at all. I had 3 more sides to do like that. The second side of the first angle, and then 2 sides on the second angle. So it's just, lather, rinse, repeat for the rest of these cuts. And I did measure the overall width and set the length of the second angle. I picked the shorter of the two and then made the lengths of the 2 angles match. It wasn't critical what the lengths were. They just had to match for ease of operation later. Some of you may recognize these little slug cutters that were made for mag-based drills. They have a really short shank on them, but I'm going to try to use it in the 3/4 inch collet here to punch a hole in the steel angle. I got to remove the factory goop here on the edge. So this is a brand new piece, never been tried. Just going to manually peck it down. One thing I don't like is this has a very short stub. I should technically be making an extension for this with a set screw on the side, so I'll make that a future project. I didn't know it at the time, but the table feed motor in the mill is causing a lot of audio feed noise that I'm only hearing as I'm editing the video, so apologize for that throughout this. You can see that from the back side, these angles truly were just scrap. So I squared off the outside edges. This is it's a woodworking stop, so we're going to find out how accurate it is. I set 0 on the back edge and the side by using a 3/4 inch diameter end mill. So radius of that is 0.375. So to step over from the back edge, I wanted a center line of 1.75 up from the back edge. The angle plus the 3/8 radius of the cutter is 2.125 on the y-axis. Now on the x-axis, the width of these angles came out to be 4.360. So 2.180 plus the radius, 2.555 from this left edge. This gives me the center of this plate. So we're going to turn this on. I'm going to use a special cutting lube that for tapping, and this was recommended by the place that sold me the slug cutters. It's just goopy and it stays in place. So we'll just peck through this manually. Cutting very easily. Almost through. And we're through. Now that's a 1-inch cutter. Let's see what size hole it gave us. Wow. 2 thousandths over. So our target hole diameter is 1.375. It's now 1 inch. So what we have to do is subtract the diameter of the cutter, which is a 1/2 inch, leaving us 0.875. And that's the diameter that we have to swing, so the radius of that is 0.4375. I'm going to dial up that offset minus about 10 thousandths and then plunge the cutter through and walk a circle. $100, $200, $300, $400, 4.1, 2, almost 4.300. That's a fairly hefty cut, but I'm going to keep the rotational RPM fairly slow, and let's see if we can do this in one pass. now we turn the head on, and I'm going to be running the head at 1/2 RPM.
So a little explaining is in order. I'm staring at this thing cutting, and it took me a few seconds, actually more than a few seconds, to realize something's wrong. It's just heading off in the wrong direction. So I stopped the cut, and when I examined it, what I saw was that the head was offset a different amount than what I dialed in. So that leaves me to conclude that I had some arbitrary amount of offset in the spindle before I started this. I did not check to see that the spindle was on 0. And the angle of the spindle, was just, 47 degrees or something strange. So when I added additional offset and then engaged the rotary head, it just started, cutting off on a diagonal and ruin that side of the piece. Luckily, I can flip it and salvage the situation.
So after that screw up that you just witnessed, rule number 1 for me when working in this mill is going to be, before I leave it, always bring the offset back to 0. And I'm going to 0 it. I'm going to run the head around here so you can see. And I'm going to 0 it on the vernier. So we're going to be coming out 80, 90, 0. Let's do that again. When this is 0 and that is 0, even if the head is pointing in an arbitrary direction, the cutter is still on 0. Another good thing to do would be to bring the head around to a 0-degree angle of rotation. So that is on 0. And that way, if we indicate the spindle to locate an edge or a hole, everything is going to be zeroed up for us, and we won't walk off and ruin the part like I did on that first piece. Plunge through first. Okay, engaging the head, 1/2 RPM. I'm going to measure this, see where we're at, and then we'll dial in a finished pass or 2. Looks like 1.357. So by the numbers, that's another 9 thousandths on the diameter. I'm sorry, that's another 9 thousandths on the radius. And I'm going to dial that in while the head is in motion. I'll tell you, that looks right on the money. When you press a bronze bushing into a hole, you have to chamfer that and just shave the edges of the bushing and destroy the press fit. Also, it's normal to see a little bit of oil weeping out because you'll actually be forcing oil out of the pores of the bushing. The next thing that happens is the bore of the bushing compresses basically the same amount as the press fit. So for a 3/1000 press fit, that bore will have collapsed 3/1000, and you should bore that out. A lot of shops want to go and just use a flap wheel, but that leaves abrasive particles embedded in there. So we're going to put this back in the fixture on the same center and then touch up that diameter to be a clearance fit to the shaft that's going in there. Target diameter for this is 0.2525, so I'm going to come down close and walk it and see if it looks like it's tracking true. Looks pretty good. I'm going to come on down through it. Now, because I'm trying to creep up on this, I'm not quite there. Let's see if we can do a test fit with the mating part. Looks like it's very close. I'm going to try to go for about another 1/1000 on the diameter. It's a little tricky because that's only a 1/2,000 increment on the radius, so I'm splitting, you know, my finest division on the scale. Very, very little play. That's the fit I'm looking for. Now, one of the things I want to do is put a radius on these two outside corners, which are going to be sticking out, and I don't want to run into them. Now, to set up and do this for any other mill, you got to get out the rotary table, and you have to clamp the part down with your center of your radius axis on the center of the rotary table, which means reclamping it to do this one. But it's a pretty easy to do on the 2D. And what I'll do first is I'm going to dial the head around to 90 degrees from 0. And at 90, that puts my spindle offset in this direction. Okay, the next thing I'm going to do is to decide what kind of radius I want to put on. And let's do a 1/4 inch radius, just because it sounds good. So what I would do is I'm going to use the X, and I'm going to come in to where the cutter is centered 1/4 inch from the edge of the piece, and with a 1/2 inch cutter I'm already a 1/4 inch offset, so I need to move a 1/2 inch. on the DRO. Okay, now my cutter is a 1/2 inch inboard of the piece. Let's zoom out so you can see the DRO in the corner. Same thing with the Y. I'm going to set my Y at a 1/2 inch. So I got a 1/2 inch and a 1/2 inch. Now I want to offset the cutter, and the cutter is a 1/4 inch inboard, the center line, and a 1/4 inch inboard. I have to come out 1/4 inch for the diameter and another 1/4 inch to bring this edge flush with the edge of the part. And of course I'm going in the wrong direction. Plus a thousandths. Now what I'm going to do is I'm going to spin the head around 180 degrees. Now that's 270. Let me get right on it. There's 270. I should be able to feed down with the quill and be essentially tangent with that edge. Now the direction I engage the head matters here. If I go the wrong way, I'm going to ruin the part. So I believe I need to come forward. Nope. I need to go the other way. So I'm coming into the cut. And what I'm going to do a practice run here. I'm going to rotate until I get near 90 degrees. That's 180 on this dial. And if I am good and I stop right there, I won't ruin my part. Okay, I set the head at 1 RPM, so it should take 15 seconds to make that cut. Watching my dial up here. I'm going to stop when I get close. Feed the rest of the way by hand. And come up. Nothing could be simpler. Now because I left that 1/1000th additional radius here, I've got a tiny blend that I have to do. Not a big deal. Now knowing the length of the part, I can traverse down to this corner, plunge down and make the second cut. I should be able to take my X to 3.858 and walk that second radius. Okay, let me put the head on, or the camera on a different viewpoint for this for you. On. One of the things I think a lot of people underestimate when they get into machining is the cost of tooling. Obviously you have your machine costs, but to do a number of operations, you start to have to accumulate all kinds of tooling. So one of my favorite fasteners is the socket head cap screw. And a socket head cap screw, if you don't want them sitting up above the surface, requires a counterbore for the head to be flush. And so there's counterbores sized for every socket head cap screw, both English and metric. Now these are all junk, but I don't have counterbores for all the socket head cap screws. But one of the nice things that the 2D does for you, the Kearney and Trecker 2D, is you can take a 1/2 inch end mill and you can make a hole and a counterbore for any size socket head cap screw a 1/2 inch or over. And if you have a 3/8 end mill, this is a 3 flute, would be really good for aluminum. You could do your 3/8 fasteners or 10 millimeters and above, all with just one piece of tooling. Holochrome has a nice chart that you can consult, and for a 1/2-13 screw, it shows you that the maximum head diameter is 3/4 inch, maximum shank diameter is a 1/2 inch. Then if you come down here, it gives you the recommended sizes for the clearance drill, which is 5/31, 32nd over a 1/2 inch. And the counterbore diameter for the head is 0.797, maximum of a 1/2 inch deep. So with a 1/2 inch end mill, we can plunge through the material. We can dial in a very small circle of 1/64 of an inch and walk that circle around and end up with a clearance drill for the shank of 5/31. And the same way, I don't have the math done in my head, we can offset the head, plunge in, and make a counterbore all with that same tooling set. We don't even have to change the tool. We can do it all in one shot, and I'll show you that now. First we'll plunge through and make a hole, and I barely have enough length on this cutter to do it, but we'll run with it. I'll just back it off to clear chips frequently. So first the pilot hole. So it became obvious in a hurry that we're not going to plunge through 1¼ inch thick aluminum with a 4 flute end mill. So let's change out to a 3 flute, which I have in 3/8 diameter, and we'll do this operation with that one, start to finish. Okay, let's see if this behaves a little better with a 3 flute end mill. Let's clear these wispy chips before they hit the camera. Now, the counterbore diameter is 0.797 and the depth is a 1/2 inch. So the first offset for the head is we're trying to achieve a diameter of 0.797 minus the 375 cutter head divided by 2 gives us an offset of 0.211. So 100, 211. Now I'm going to plunge down and until I touch the surface, and then I'm going to start cranking in my depth. Now I have a depth of 100 thousandths per crank. So there I'm touching at about 60. So let's take it down 300 thousandths, and then we'll do the final 200 thousandths on the second go around. That was 1 RPM. Let's try 1/2 RPM. This would be a good operation for air and coolant. Second rotation, we've got to go full depth. The head is done, counterbore. So we're going to run the cutter back to 0. And now our offset for the clearance for the shank, which is a very small offset, is 0.078. So not even a full rotation. 30, 40, 50, 60, 70, 8. So on this one we plunge down through and walk a circle, and we should be able to go faster again because we're cutting much smaller circumference than we were with the counterbore. So there's our counterbored hole. I'm about 1/1000 under 499 on depth. Target was 797. I'm about 798, 799. And the 531 is about 532. There's your fit per the holochrome chart, and that's the standard clearance over the bolt diameter. Bolt circles are really easy to do with this rotary head mill because we've got this precision scale on the head directly, reading in degrees, and you have control of the head 3 degrees per rotation of the hand wheel, with a vernier on the hand wheel as well. So let's say we wanted to have a 1-inch bolt circle with 6 bolt holes centered on this feature. What we would do is we would dial in the offset of a 1/2 inch. Previously having zeroed the head on the feature, and we are sitting right now at 60 degrees, and we just spot our holes. Index the head. And so we have our 6 bolt hole pattern centered about that feature without any fussy setups, and no rotary table. Now if you use a lot of flathead cap screws, and I am not a fan of flathead cap screws, but when you have to use them and sink the head flush, you have to have a chamfering tool, usually an 82 degree countersink. This is a 90 degree countersink, but for this demonstration, just pretend it's an 82. And if you're doing all your hole in one shot, there's no additional setup, but I had to zero in on this hole, and then I want to chamfer the top to account for a flathead cap screw. So there are a couple ways you can do it. You could plunge and offset while the head is rotating, or you could dial in the offset and then use the quill down feed to increase the depth of cut. I'm just going to dial over here until still going to put the point of the countersink tool into the hole, and then I'm going to start the spindle, bring down until we cut, and engage the cutter head. At each rotation, I'll increase the depth of cut a little bit until we get the diameter we want. This is one of those instances when I'm using the full rotation speed of 3 RPM because it's such a small diameter. And we'll let it do a spring pass to clean things up. And it makes a very nice, clean countersink for you because it's it's milled. It's not a plunge cut. It's not a form cut. If you don't have a rigid machine, I've seen some countersinks for 3/8 and 1/2 inch fasteners that are very chattery. But just with a proper chamfering tool, you can make any size countersink you want for any fastener you want. So it's the end of the day, and I'm going to return my spindle offset to 0, which I do in the direction towards the 4-inch vernier. That way when I set up for the next cut and I come down with the quill, I know that I am zeroed and not in some random orientation. Rule number 1, never leave the spindle offset at the end of the day. Rule number 2, always return the spindle offset to 0 at the end of the day. You can see what happened with this in that one cut. I had set up for enlarging an existing hole and zeroed in on it, and then when I dialed in my offset, I had already had less than 1/2 inch, but I had some offset on the spindle, some random orientation of the head. And when I dialed in more offset and then engaged the rotary head, it started walking off in a direction that I hadn't anticipated. So these are the 2 cardinal rules for this mill, and I am going to do my best to abide by them from this point forward. Hope you enjoyed that, and more projects coming up on the KMT rotary head mill.